So in number 51, we have a wood cylinder of mass 0.25 kilograms and length zero point 0.1 meters with 10 turns of wire wrapped around it longitudinally so that the plane of the wire coil contains a long cylindrical axis of the cylinder. The cylinder is released on an inclined plane and inclined at an angle theta to the horizontal with the plane of the coil parallel to the inclined plane. If there is a vertical uniform field of magnitude 0.5 teslas, what's the least current through the coil that keeps the cylinder from rolling down the plane? So what we've got here is an interesting case. We've got the force of gravity trying to act down at the center of mass of this thing, and the pivot point is actually the point of contact between this and the cylinder. The torque, if you remember, is just going to be the radius times the force of gravity, or cross product. Or in more general terms, radius times mg, force of gravity, times the sine of the angle. In this case, we're given the mass, so 0.25 times 9.81 gives us, so mg becomes this, times r times the sine of theta. We're not given the radius and we're not given theta, so we can't solve this any further. So now let's take a look at this. If you remember, a current-carrying coil in a magnetic field is also given by this, where N is the number of turns, I is the current, A is the area, and that's across the magnetic field. Now the area vector is actually given by the area that's normal to this piece right here. So the area vector would be pointing up like this. And most of you can sort of see this angle here, theta, is going to be related to this angle down here, theta. So I can immediately rewrite this as NIAB sine theta, where theta is the angle here. We can actually plug in some numbers. The number of turns, N, is 10. And then the area is going to be the length of this, which is 0.1 meters, times double the radius. If you think about r being here, so my width is going to be 2r. Magnetic field is given as 0.5 teslas times sine of theta. Reducing that down, it actually comes quite nice. We just get the torque is equal to IR sine theta. Setting the two equal to each other, we know the torque that's trying to roll it down the slope must be equal to the torque generated by the magnetic field. R, of course, cancels along with sine theta, giving us just I is equal to 2.45, or in general terms, the current required, 2.45 amps. Hopefully this helps and makes some sense. Good luck.